In this last video, I'm going to finish out the lecture notes on double integrals over general regions. So I'm looking at page 3 of the lecture notes. I'm looking at this example here. We had this. Okay, it said evaluate this and sketch the region you're integrating over. Okay, so when you go to evaluate this, okay, first let's sketch this region. Okay, so this region, this is y, as you know, because it has to match. So we have y equals x. Everyone should always have that graph memorized. And then we have y equals 1. Okay, and because x is being bounded between 0 and 1, this is your region D. Okay, when you go to integrate this currently, how would you integrate that if y is a variable? You don't have a direct technique. Okay, be prepared for this to happen. Okay, when I give you a quiz on this, there will be some questions that you're going to have to think outside the box. All right, so we encounter a problem. Well, what do we do when we encounter a problem? We solve that problem, right? We're mathematicians. So what we're going to do instead is we're going to switch this around so that instead of first respecting y, okay, so by first respecting y, as you know, you would have a vertical rectangle. Okay, instead what we're going to do is we're going to make our rectangle horizontal. Okay, let's look at why we're going to do this. So if we do this, what does that mean about sine of y squared if we're respecting x? I'll give you a minute to think about that. If we're integrating with respect to x first, what does that mean about sine of y squared? Okay, so hopefully you paused the video and thought about it. So that means that sine of y squared is a constant. So when you integrate this, you would just get sine of y squared x. All right, so we're going to change our bounds. So instead of being in terms of y, we're going to make this x equals and x equals. Okay, however, this is y equals x, right? So that's x equals y. That's going to be your right curve. Okay, your left curve is going to be the y-axis, which has the equation x equals 0. And now your bounds are just going to vary in terms of y. Well, your upper bound for y is going to be y equals 1. The lower bound is y equals 0. So you continue integrating this. We integrated, and now we have to substitute in our bounds of integration. So I have to replace x with y. So we have sine of y squared times y. And then the other lower bound is going to make that 0. All right, sine of the quantity y squared times y is not sine of y cubed. Okay, please don't do that. However, when we go to integrate this now, we're going to have a technique, okay, that we learned in Calc 1. What technique is that? That's correct, u substitution. So we're going to let u equal y squared, then du is 2y dy, so a half du. Well, actually, I don't have to go back to my u. I could change my bounds of integration. That's always easier, okay? Don't want to set an example for you, a bad example for you here, poor example. So if I change my bounds of integration in terms of u, I don't have to go back to my y. So let's look at what u is going to become. So u is y squared, so u is 1. Oh, how convenient. They stay the same. So this new integral is going to be having the bounds in terms of u, and the sine of y squared is going to be sine of u. I need to replace the y dy. Y dy gets replaced with du over 2. Okay, so now when you integrate this, what has a derivative of positive sign? Negative cosine. 2 is just a constant. Substitute in your upper bound, or you could switch your bounds around and make that a positive, up to you. So we get negative cosine of 1 over 2 minus negative cosine of 0 over 2. And as you know, cosine of 0 is 1. So that's going to be plus 1/2 negative cos 1 over 2. All right, so let me pause this and write up the next part. All right, this is the first time I've actually entered a second page, so I'm not sure how this is going to work when I upload this video. So this is a little bit of an experiment because I want to know what's going to happen. Anyway, so on page 4 of the lecture notes, these are just the properties of double integrals. They should all make sense to you. So if you have two separate functions and you are integrating over some region, the sum of those surfaces, it would be the same as just integrating each of those surfaces over your domain and adding them. Okay, if C is a constant, constants factor out of everything in calculus. Okay, looking at C, if you have some region that can be divided up into two subregions that are disjoint, that means they do not intersect, you can split them up, and sometimes that will be very convenient. Okay, I'll give you an exercise for homework to do on that. D is very handy. As you know, math problems have other math problems embedded within them, so if you ever have 1 dA over some region D, you can just get the area of that region, except your answer will be in units cubed. All right. E is very interesting. It's sort of like a squeeze theorem. Not quite. But you're going to be bounding, all right, some function. So if you have some surface and it's bounded between two other surfaces, one below, one above, for all A, this just means for all, okay? Kids at this level, you are expected, to be able to handle that. For all A that are elements of your domain, then the volume below the surface, that's below the surface f of xy, will be less than or equal to the volume of below the actual surface. And since that surface is below M, that will be less than or equal to the volume below that surface. Okay, let me pause and write up an example. All right, let's look at the last problem in the set of lecture notes. So we're estimating the volume of the surface e to the sine x cosine y over the disk centered at the origin of radius 2. Okay, as you know, okay, this area is equal to pi r squared, so that's just equal to 4 pi. Okay, keep that in mind. All right, well, since -1 is less than or equal to, what's that mess? All right, so since -1 is less than or equal to sine x less than or equal to 1, and -1 is less than or equal to cos y less than or equal to 1, that means that the product sine x cos y has to be bounded between -1 and 1. All right, therefore, e to the sine x cos y must be bounded between e to the -1 and e. So when we want to approximate this volume, if we use this property that we had from part E, I realized I forgot to mention one thing. So if you have a constant, okay, m is some constant, dA, when you're getting this volume is just m times the area of D. Okay, so we're going to be using this property. Same thing if this is a capital M and it's a constant. This would just be M times the area of D. So over here, I know the area of D is 4 pi, right? So that means that the integral of e to the sine x cos y dA is bounded between 4 pi e and 4 pi over e. So you could imagine that this is definitely an advantage to be able to approximate volume. Okay, thank you for your time.